Let's go back to number systems. The fourth number system that we want to discuss are the rational numbers, and we use the letter Q to denote the rational numbers with. These are all numbers that can be written in the form a over b, in other words as a fraction, where both a and b are integers and b cannot be 0, since we can't divide by 0. Now all the integers are rational numbers, since we can write them as fractions. For example, 0 can be written as 0 over any number, for example 3. 1 can be written as 1 over 1, 2 as 2 over 1, negative 3 as negative 3 over 1, etc. Note that the natural numbers form a subset of the whole numbers, which form a subset of the integers, which form a subset of the rational numbers. Here's a more complete list of the rational numbers. We saw previously that the integers are all rational numbers, since we can write them as fractions. Then any fraction, including mixed numbers, for example 3.5, would be rational. 3.5 we can write as a fraction as 7 over 2. Another example, negative 4 and 3/5 can be written as negative 23 over 5. Then all square roots of perfect squares, for example the square root of 1, the square root of 4, negative the square root of 9, all of these can be written as integers and hence as rational numbers. We can also include cube roots of perfect cubes. For example, the cube root of 27 equals 3, which is an integer and hence a rational number. Then all terminating decimals, for example 1,75, which can be written as 175 over 100, negative 3,874, which can be written as a fraction as well. Then all non-terminating but recurring decimals, for example 0.3 recurring and negative 0.018 recurring. The next number system that we'd like to look at are the irrational numbers. We use a symbol Q minus for the irrational numbers. And the irrational numbers are all the numbers that can't be written in the form a over b, where both a and b are integers and b isn't 0. In other words, all numbers that are not rational are irrational. The most famous example, of course, is pi, but the irrational numbers also include all square roots of positive numbers that are not perfect squares, and all cube roots of numbers that are not perfect cubes. Then it also includes, in general, all non-terminating, non-recurring decimals. So let's look at your answers to this question. We have to say whether each of these numbers are rational or irrational, and we have to give a reason for our answer. In A, we have the square root of 41. Now, this is an irrational number, and the reason is that it's a square root of a number that's not a perfect square. 41 isn't a perfect square. Then we have the negative square root of 64. This is a rational number, and the reason is that it's a square root of a number that is a perfect square. 64 being a perfect square, and the square root of 64 is 8, which of course is a rational number. Then in C, we have the square root of 7 over 9. This is an irrational number, and the reason is that it's a square root of a number that's not a perfect square. Although 9 is a perfect square, 7 isn't a perfect square. Then we have the cube root of 23. It's an irrational number. And the reason is that it's a cube root of a number that's not a perfect cube. 23 is not a perfect cube. Then in E, we have the cube root of negative 64. This is a rational number. And the reason is that it's a cube root of a number that's a perfect cube. Negative 64 is a perfect cube, and the cube root of it is negative 4. Then in F, we have negative 0,1 recurring. So this is a rational number, and the reason is that it's a non-terminating, in other words, it continues forever, but recurring decimal. So there's a pattern after the decimal point or the comma. So 0,111 and so forth. Then 6.93 recurring. So this is 6,93, 93, 93, etc. It's a rational number because it's a non-terminating but recurring decimal. So the pattern repeats after the decimal. Then we have 11,184. This is a rational number, and the reason is that it's a terminating decimal. In other words, it ends. We just have 184 after the decimal, and it doesn't continue. Then we have negative 4,184,32571, and so forth. It's an irrational number, and the reason is that it's a non-terminating, in other words, it continues forever, and non-recurring decimal. Non-recurring means there's no pattern after the decimal. Then we have the square root of 1 and 7/9. This is a number that can be written as a square root of 16/9. Now, this is a rational number, and the reason is that it's a square root of a number that's a perfect square. 16/9 is a perfect square, and the square root of it is 4/3. Then we have negative 5/8, which is rational, and we know that any fraction is rational, whether negative or positive. Then lastly, we have pi. Now, pi can also be written as 3,141592, etc. We know that pi is an irrational number, and the reason is that it's a non-terminating, it continues forever, and non-recurring decimal. And once again, non-recurring means that there's no pattern after the decimal point or the comma. So in this question, we have to state whether each of the numbers listed are rational or irrational. In A, we have pi. We know that the number pi is irrational. And the reason for that is that it's a non-terminating, in other words, never-ending, non-recurring decimal. In other words, there's no pattern after the decimal point or the comma. So pi, therefore, is irrational. Then in B, we have 2 pi. So we're multiplying the number pi by 2. When we multiply this number by 2, it's still going to be non-terminating. And there still won't be a pattern after the decimal. So basically, if you multiply an irrational number, such as pi, by a whole number, we'll still get an irrational number. So the number
2 pi then is irrational. Then in C, we have pi divided by 2. Once again, if we divide pi by 2, we'll still get a non-recurring, non-terminating decimal. So pi by 2 will still be, or will also be, irrational. Then in D, we have 2 plus pi. So basically, we're adding 2 to this number. So it's going to become 5,14159, etc. In other words, it will still be non-terminating and non-recurring. And hence, 2 plus pi is also irrational. Then in E, we have 2 plus the square root of 5 divided by 3. Now, we know that the square root of 5 is irrational. If we add 2 to the square root of 5, by the same argument as in D here, the numerator here will be irrational. So we're then dividing an irrational number by a whole number, and by the same argument as in C, this number will be irrational. So here we have to say between which two whole numbers each of these irrational numbers lie. In A, we have the square root of 11. Now, when we have a square root in this context, it really helps to list the first few perfect squares. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so forth. So the first few perfect squares will be 0, 1, 4, 9, 16, 25, and so forth. The number 11 lies between the two perfect squares 9 and 16. So that means that the square root of 11 will lie between the square root of 9 and the square root of 16. So the square root of 11 is greater than the square root of 9, but less than the square root of 16. The square root of 9 is 3, and the square root of 16 is 4. So now we've answered the question. The irrational number, the square root of 11, lies between these two whole numbers, 3 and 4. In B, we have the square root of 2. Now, the number 2 lies between these two perfect squares, 1 and 4. So that means that the square root of 2 lies between the square root of 1 and the square root of 4. The square root of 1 is 1, and the square root of 4 is 2. So once again, the irrational number, the square root of 2, lies between these two whole numbers. In C, we have the cube root of 9. Now, when we have a cube root in this context, it helps to list the first few perfect cubes. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64 and 5 cubed is 125. Now, the number 9 lies between these two perfect cubes. It lies between 8 and 27. So that means that the cube root of 9 lies between the cube root of 8 and the cube root of 27. The cube root of 8 is 2, and the cube root of 27 is 3. So the irrational number, the cube root of 9, lies between these two whole numbers, 2 and 3. Then lastly, we have the cube root of 67. Now, the number 67 lies between these two perfect cubes, 64 and 125. So that means that the cube root of 67 lies between the cube root of 64 and the cube root of 125. In other words, it lies between 4, which is the cube root of 64, and 5, which is the cube root of 125. The second last number system that we want to look at is a set of real numbers. We use the symbol R to denote the real numbers with, and it consists of all the whole numbers, natural numbers, integers, rational, and irrational numbers together. Note that the natural numbers, the whole numbers, the integers, and the rational numbers are all subsets of the real numbers. The irrational numbers form a separate subset of the real numbers. So here we have to say whether each of the numbers listed below is a natural number and or a whole number and or an integer, rational or irrational, and whether it is real. Now, before we look at these numbers, let's just list the first few number systems. We have the natural numbers, 1, 2, 3, etc. Then we have the whole numbers, so it's the natural numbers, but including 0. And then we have the integers, which are positive and negative whole numbers, including 0. Then also important to note that if a number is a natural number, or a whole number, or an integer, it will automatically be rational. Since the natural numbers, the whole numbers, and the integers are subsets of the rational numbers. Then if a number is any of these, whether it's natural or whole or an integer or rational or irrational, it will automatically be real as well, because all these number systems are subsets of the real numbers. So in A, we have the number 0. Now, 0 is clearly a whole number as well as an integer. Then we said if it's a whole number or an integer, it will automatically be rational. And if it's any of these numbers or number systems, then it must be real as well. Then in B, we have the number -7. It's not a natural number, nor is it a whole number. It is an integer though. And if it's an integer, it must be rational, and hence real as well. Then in C, we have the number 15. It's a natural number. It's a whole number as well. And it's an integer. And hence it must be real as well. Then in D, we have 3/4. This is a fraction, so it's not a natural number, nor is it a whole number, nor is it an integer. All fractions are rational. So it's rational, and hence it must be real. Here we have -2.5. This is a mixed number, but we know that we can write mixed numbers as improper fractions. This is -5/2. And it's clearly not a natural number, it's not a whole number, neither is it an integer. Of course, because it's a fraction, it must be rational and hence also real. Here we have the square root of 81. We know that this is 9. It's a square root of a perfect square. And 9, of course, is a natural number. It's a whole number. It's an integer. And remember that all integers are rational numbers as well, because we can write them as fractions. So it's also rational and real. Then in G, we have negative the square root of 17. It's clearly none of these three number systems, or in any of these three number systems. It's a square root of a number that's not a perfect square. And that means that it's irrational. So we can either write Q minus, or we can write Q prime. Any of these two symbols we can use for irrational numbers. So it's irrational, and we know that all irrational numbers are also real. Here we have the cube root of -64. We can work this out. The cube root of -64 is -4. Now, -4 is not a natural number or a whole number. It is an integer, and because it's an integer, it must be rational as well, and hence also real. In I, we have the cube root of 3. 3 is not a perfect cube, so we know that it's irrational. Remember that the cube root of a number that's not a perfect cube is irrational. And all irrational numbers are also real. In J, we have the square root of a mixed number. We can first convert the mixed number to an improper fraction. So 1 7/9 we can write as 16/9. And this, of course, is the square root of 16/9 is 4/3. Now, 4/3 is a fraction, so it's none of these three number systems. We know that all fractions are rational numbers, and hence also real. In K, we can do the same. We can write this mixed number as an improper fraction. So this is 11/4. So we have the square root of a number that's not a perfect square. And of course that means that it's irrational, and hence also real. Then we have 7,251. So this is a decimal that is terminating. Any decimal won't be a member of any of these three sets. But a terminating decimal is rational. So it's a rational number, and hence also real. In M, we have 11,3 recurring. This is a non-terminating but recurring decimal, and hence it's rational and also real. Then we know that pi is an irrational number. It can't be written as a fraction. So it's irrational and also real. Then lastly, we have another decimal. It's non-terminating, but there's no pattern after the decimal point or the comma. So it's non-recurring. And we know that a non-terminating, non-recurring decimal is irrational. And it's also real. So let's look at your answers to this question. We have to place a tick in the correct column or columns. 2 3/4 is a mixed number, and we can write it as a proper fraction. So 2 3/4 can be written as 11/4. So it's a fraction, and hence it's a rational number. Of course, the natural numbers, the integers and the whole numbers do not include fractions. Then all rational numbers are also real. 7/10 is a fraction and hence a rational number and also real. Then we have the square root of 3.5, so the square root of a mixed number. 3.5 we can write as an improper fraction, and we can write it as 7/2. So it's a square root of 7/2. Now, 7/2 is not a perfect square. So we have the square root of a number that's not a perfect square, and hence it's irrational. All irrational numbers are also real. Then we have negative the square root of 64. 64 is a perfect square, and the square root of 64 is 8. So this is -8. -8 is an integer. Of course, it's not a natural number or a whole number because of the negative. Now, all integers can be written as fractions. So it's also a rational number and hence also real. Then we have the cube root of 0,027. Now, 0,027 can be written as 27/1000. So basically the cube root of 27/1000. Both 27 and 1000 are perfect cubes. So the cube root of 27/1000 is 3/10. So once again we have a fraction which we know is rational and hence also real. Then 2 pi. Pi is an irrational number, and we know that when we multiply an irrational number by a whole number, we get an irrational number. So 2 pi is irrational, and all irrational numbers are real as well. Then we have 0,312. This is a terminating decimal. Now, a terminating decimal is rational. In other words, it can be written as a fraction. Of course, the natural numbers, the integers and the whole numbers do not include decimal numbers. Then, because it's rational, 0,312, it's also real. Here we have a non-terminating but recurring decimal, which we know is rational and also real. The last number system that we want to look at are the non-real or imaginary numbers. These are even numbered nth roots of negative numbers. For example, the square root of negative 1, the fourth root of negative 3, the sixth root of negative 4, etc. It can also include the square root of negative pi, in other words, the square root of a negative irrational number, and the square root of negative 3 over 2, which is the square root of a negative fraction, and the square root of a negative decimal. You should note that odd-numbered nth roots of negative numbers are real. For example, the cube root of negative 3 and the fifth root of negative 1 are both real. Before we complete this topic with the last question, we want to look at the special property of the number 0 called the division property of 0. It says that when we divide any number by 0, the answer is undefined. In other words, any number a divided by 0 does not exist, and we often use the abbreviation DNE. For example, 3 divided by 0, negative 1,342 divided by 0, the square root of 89 divided by 0, and pi divided by 0 are all undefined. Let's look at your answers to the last question. We have to complete the table by placing a tick in the correct column or columns. We have 0 divided by 3. Now 0 divided by any number is 0, which we know is real. Then we have 3 divided by 0, and we know that any number divided by 0 is undefined. Then we have the square root of a negative number, which we know is non-real. The cube root of a negative number is real.